I'm going to kick off tonight's lightning talks and hand it over to Chuan Lee, who is a founding team member and chief scientific officer at Lambda.
Today, I'm going to talk about how to solve 2D puzzles with small LLMs. This is a work of David Hartman, who is a researcher at Lambda, and his friend Jan and Daniel, who are both PhD students from University of Mainz. They three actually was the team that won last year's ArcAGI challenge. So let me see if I can. Yeah, if you are not familiar with the ArcAGI challenge, don't worry, I'm going to talk about it in a bit. I'm also going to talk about how some of the community's best practice of tackling this kind of problems, and also what our team did differently to win the competition. Just like for the record, we are not a code engineer, we are not compiler engineer, so we didn't do any low-level like kernel optimization, but I feel like we are chasing the same goal here in terms of we are trying to solve a challenging problem with less resource. So hopefully this talk gives you guys a slightly different perspective. All right. So what is the ArcAGI? Arc stands for Abstract and Reasoning Corpus. Intuitively, you can think of ArcAGI is sort of like an IQ test for AI. Here's an example. Basically, you are asked to solve some 2D puzzles. In this case, you are given some like examples. In the first three columns give you the input and output, and then you are asked to generate an output from the fourth column. And in this case, you are supposed to fill in the empty box with yellow. So why this is fun and a challenge? Well, to begin with, there's a lot of like cognitive tasks need to happen here. You need to recognize the pattern. You need to recognize the mapping between the input and output with only a few examples. So that's already challenging enough. And this is also in particularly challenging for LLMs, because you can imagine LLMs works in 1D space. So in order to have LLM work on this kind of problem, you need to flatten the 2D grid. And this flattened operation sort of like messed up some of the spatial relationship between the cells and make it harder for LLM to learn. Also, it's very easy to make the problem much harder by just simply scale up the resolution and also impose some kind of long-range structure, for example, global symmetry. And overall, this task is just very brittle in the sense that everything has to be pixel-wise perfect. If you make one single mistake, the answer is wrong. And on top of that, I think this is most interesting for today's topic, which like the organizer actually imposed a resource limitation during online testing stage. You can only use 2 NVIDIA T4 GPU for 12 hours to run your solution. And this means you cannot run very big models or run the model for a very long time. So to put all the challenges into a context, this is a graph showing the relative performance of AI versus human across different type of tasks. And the yellow curve is the best AI algorithm for ARC. You can see throughout the years, there's definitely some progress, but the progress is at a much slower pace compared to other tasks. Where you see the blue curves basically shows in other tasks, the AI quickly catch up with the human and sometimes even surpass human performance. So what our team did last year is to sort of like bring this yellow curve up to speed. So in the rest of the talk, I'm going to discuss like how we did that. Yeah, before diving into our own method, just want to do like touch on a few best practice of like how community has been tackling this problem in the past. I'm going to focus on LLM-based approach because this is really popular and this is also something we use. As you can imagine, LLM are not trained for this kind of task. They are trained for natural language task, and this is sort of like a pattern recognition task. So intuitively, you want to collect more data and fine-tune the model. So there's a lot of people doing that. And you can get new data from different sources. You can have like synthetic data, program generated ARC-like problems and answers. You can have data augmentation. But the one thing I want to particularly highlight is this thing called test time training. This is very interesting in the context of ARC challenging because ARC allows you to upload code instead of model weights. So that means during this online testing stage, you can actually run fine-tuning in addition to the final inference. So this gives you the opportunity to basically fine-tune the model weights for individual tasks. You're actually making a separate model for individual tasks. Obviously, this brings more compute, but you got a much better model performance on these tasks. So if you do all this fine tuning with data from different sources with some engineering trick I'm going to mention later, you're actually able to improve the performance from the baseline below like 20 points to about 40 points. So that's actually pretty good, but we still need another 20 to 30 points improvement to win the competition. So what did we do? Well, this is something we did not do. We did not do prompt engineering. We did not do train of thought because we just asked LLM to do next token prediction straight out of box for the answer. And we cannot afford running large model. The first thing we did is to try to optimize the efficiency across the board. And the biggest change we made is actually remove most of the token from the vocabulary. We removed 99.95% of token from the dictionary, only keep 64 tokens. And this does not only reduce the memory requirement to run the model, but also helps the model to focus on this kind of puzzle solving pattern recognition task instead of thinking this is a language task. And this is an example of how to represent the 2D grid puzzle by the remaining 64 type of different tokens. We have numbers to represent the different colors. We have special tokens for the beginning of a sentence, end of a sentence. And we also have a special token to separate input from output and do the new line switch. We also did a very aggressive quantization with 4 bits for the weight, with quantized LoRa for fine tuning, and we use gradient checkpointing. So all these reduce the memory requirements, so we can actually run test time training during the submission. And we also use like Onslaught as the fine tune library. Big shout to Onslaught. So with all this engineering trick together with the fine tuning, gave us the so like from 20% to 40% improvement. However, as I said, we still need to get another 20 to 30% to win the competition. So what did we do? The big lesson learned here is we just need to accept like LM can make a mistake and will make mistakes. Just think about it. Like the best model we had back then gave us 40% accuracy. That means LM will more likely to give you a wrong answer than the right answer. So let's say just accept the fact. So how about let's just like LM roll out more potential answers. So there's a higher chance to have some of the answers being correct, and try to spend more time to look at the answers and pick the right one. And then what we find along the way is, despite LM being a mediocre generator for the answers, it actually can do a very decent job as a discriminator that it tells a good answer from the bad answer. Yeah. So how do we implement this? First, we need to get a bunch of proposals for the correct answers. What we did is depth first search, try to enumerate all the possible 2D patterns. But I was joking, that would be so expensive. So what we did is we try to do early stop. While we are generating a hypothesis, we try to score the sequence generated so far. And if the score falls below a certain threshold, we do early stop. We skip the rest of the subtree and switch to a different branch. But the trick thing here is how do we score a potential answer on the fly? Well, the answer is actually we can use the joint conditional likelihood of all the previous generated tokens to use that as a score. This is basically output of LM. So we actually use LM not only as a generator, but also as a scorer. And if we do that, we are able to quickly prune the tree search and find a set of very promising candidates for the answer. Now, the question is, we have this set of candidates. How can we choose the best one? Yeah, the lowest hanging fruit is just like pick the one with the highest score. But that actually is not going to be optimal. The thing about this, we actually give LM a degenerated version of the original question. We flatten the 2D grid into 1D, and it depends on how you flatten the 2D grid. It can be row-based or column-based. The order of the token in the output is going to be different. That will give you different scores. So we think, why not just do data augmentation on both the input and output? So let the LLM look at the question and answer from different perspectives. And for each perspective, you will have a different score. And we sort of aggregate the score from all the perspective. And that gives LLM a more holistic view and give it a better chance to pick the best answer. So this is the key. If we do that, we are able to boost the performance up to 70.1%, which is the final solution that enable us to win the competition. And I also want to put this into context. OpenAI released O3 a month later, and got a lot of more improvement in terms of score, but also cost 100 times more test time compute. And this tells us two things, basically. First, the field just moves so fast, it's crazy. But at the same time, there's a huge amount of opportunity to basically optimize the effectiveness and efficiency of open source models for very specific tasks. Yeah, to wrap things up, I guess this is a really interesting study that we learned a few things. First of all, it's kind of actually amazing to think LLM can actually do this, given all the challenges and the limitations. But also, we learned that in order for LLM actually to do those jobs, you have to augment it with engineering improvement, make everything more efficient, and try to leverage LLM not only as a generator, but also as a discriminator. Things like give LLM a lot of different perspective to see the problem as a whole. So all this says LLM need to be optimized or can be optimized for very specific questions. And yeah, here's a link that can give you more details of the work, including a research paper, the code, and the pre-trained models. And feel free to reach out. Happy to discuss more in details. And yeah, thanks a lot for listening. Enjoying the workshop, enjoying the hackathon.